Okay, so chamfers. A chamfer is an angle cut at the end of the shaft or an edge of a hole. Chamfers remove sharp edges, add the appearance of the part, and provide handling safety. Chamfers also enable parts to be assembled more easily, and the ends of screws and bolts are chamfered for this reason. Chamfered edges are usually cut at angles ranging from 30 to 45 degrees. Dimensions, for example, internal or external chamfers are given as an angle cut to the axis, or center line and a linear length. Two examples are shown in figure 23.7a. And then internal chamfers are given as a diameter at the large end of the chamfer and the angular dimension to one side of the diameter and the included angle of the chamfer. So these. And then that was the end of that one. So I think this is the last one. So undercuts, undercutting or necking is, as it is sometimes called, is the process of cutting a recess in a cylindrical part. Undercuts are often machined at the end of the threaded section or where a shaft changes in diameter. Undercutting or necking operations remove any material that has been left from prior machining operations, thus allowing mating parts to seat flush against each other. Necks are usually dimensioned with a leader and a note specifying the width of the undercut and the diameter of the depth. The bottom of the undercut may be square, or a radius may be specified to add strength and reduce the possibility of breakage. If a radius is required, it should be specified in a notation and the finished diameter measured at the bottom of the radius. Figure 25.2 shows two examples of dimensioning undercuts. So that's a square, and then that would be a radius. Alright, knurling is the process of creating straight or diamond-shaped pattern on a cylindrical object using special knurling tools. The knurl is formed by forcing hardened knurl rollers on the knurling tool into the surface of a revolving cylindrical part. The pressure of the knurling tool creates a pattern of straight or diamond grooves as the material is forced outward against the knurling rollers. Figure 24.3, in addition to creating a pattern on the surface of the cylindrical workpiece, the displacement of metal during the knurling process tends to increase the diameter of the knurled part. So, just like that. Knurls are made in a diamond or straight patterns. Figure 24.4, the diametral pitch of the knurling tool determines the size of the finished knurl. The distance between the knurling grooves decreases as the diametral pitch increases. A 64 dp knurl would be coarser to a 128 dp knurl, for example. The most commonly used diametral pitches for knurling are 64, 96, 128, and 160 dp. Knurling operations are often performed to improve the appearance of a part, provide a gripping surface, or to increase the diameter of the part when a press fit is required between mating parts. Straight knurls, for example, may be specified to create a tight fit between a shaft and a hole of equal diameter. Dimensioning knurls. Knurling is generally dimensioned by specifying type, pitch, length of knurl, the diameter of the shaft being knurled, figure 24.5. The finished diameter of a part after knurling may be specified if it is important to do so. If a straight knurling operation is performed to create a tight fit in a hole, for example, the minimum diameter after knurling should be specified with a dimension and notation. So that gives you the two different types there. And then this is actually what we're doing this time. Real short video, and I hope y'all do well with it.